In this video, we'll demonstrate the use of PowerFactory's state estimation function for an unbalanced network. Study case 8.0 should be active. The state estimation function is used to obtain consistent load flow results based on measurements that have been imported into PowerFactory. This is done, in this example, by estimating the active and reactive power quantities for the load objects. At the core of the function is an optimization process, whose objective is to minimize the difference between the calculated load flow results and the measurement values through adjustment of the relevant element attributes. For the purposes of this illustration, we've actually assigned true power values to the load objects. These are not used in the state estimation, but we've used them to run a load flow and obtain true results, to which we can compare the state estimation results. The reporting from the state estimation analysis allows the user to identify areas where better measurements are needed because the existing measurements are insufficient or are of poor quality. In this study case, 5 feeders are considered, and these are shown in this schematic diagram. Measurement data is made available via measurement elements, which can be set up as balanced measurements or for individual phases. Let's colour the diagram to show the locations of these objects. In this case, there are many measurements available. It's referred to as an overdetermined scenario because in fact there are more measurements available than are needed in order to determine the state of the network. There are measurements for active power, reactive power and voltage at the connection points of many of the load objects and at the start of each of the 4 subsidiary feeders. Here is a typical example. It can be seen that unbalanced measurements are provided, one for each phase. Measurements can be prone to error. This means that they can differ from the true values in the actual network. Let's look at this diagrammatically for some selected elements. This plot shows the difference between measured and true values at the start of feeder FD125. And here the active power values are shown for load 232. On the left-hand side are the measurement values, and on the right-hand side the true values. They are close but not identical. The quantities to be estimated by the state estimation function are the active and reactive powers of all the loads in the feeder. The command is found in the Additional Functions toolbox. For this LV network, we will use an unbalanced AC load flow. Here, the calculation components are selected. The plausibility check is used to identify and discard suspect data, as determined by the checks on this page. For example, for measurements connected to branches that are open-ended, there shouldn't be any large power flow. The measurement values are compared with the power rating and accuracy, with the possibility of a factor being applied to relax the limits. Implausible measurements will be ignored. The observability check is used to detect regions of the network for which insufficient data are available. On the related page of the dialog, the user can configure how the observability checks are to be carried out, and how the unobservable regions, i.e. where there are insufficient measurements, should be fixed. Finally, there is the non-linear optimization component, which optimizes the network until the best fit with the measurements is found. Part of this process is to detect and eliminate bad data. On the bad data detection page, the maximum number of bad data measurements to be handled and the tolerance factors can be set up. The state estimation process is iterative alternating between the observability analysis and state estimation until a converged solution is found. Let's run the calculation. We can now see the estimated values as well as the measurements and true values. In this study case, there's a good coverage of measurement data, and so the estimates of current and voltage seen in the top two plots are extremely good. For the power flow in feeder FD125, the estimated value is somewhat better than the measurement. And we can see that the estimates for the three phases of this load object are close to the true values. However, to have so many measurements and even many redundant measurements is not normally the case in real life. So we'll now activate study case 8.1, which provides a more realistic, underdetermined scenario. In this study case, many of the measurement devices have been made out of service, as shown by the blue colouring. Pseudo-measurement devices have been defined to replace the missing measurements. These act as low-accuracy devices which have reasonable default measurement values, but are only used for the situation where there are unobservable states. As an example, let's look at the pseudo-measurement device for load 128. We can see that it is flagged to be used as a pseudo-measurement device and that the values have all been set to 1 kilowatt. These pseudo-measurements will be used as required in the analysis. We'll now execute the command. In the output window, we can see that only 142 out of 266 states were observable, and that the pseudo-measurement devices were used in order to reach a solution. In this plot, the estimated power for the feeder is now similar to the measured value. That's to be expected because for an underdetermined scenario, the individual measurements have a greater impact on the result. This load still has its original measurement data, which is used in the estimation process, and the estimated values are again close to the true values. It can be seen that the estimates of line current and terminal voltage are not as close to the load flow results as before, but the differences are still relatively small.